Welcome back to Science's Bedroom, and this is the third reaction in this series. It's named Bernd Eistert reaction. I'll be sharing details in a short while. As you can see from the slide given here, that this reaction is basically used to increase the length of the carbon chain by one methylene group only. Like suppose if the methylene group, if the alkyl group is ethyl, then it will become propyl. If it is methyl, then it will become ethyl. Just one increase of the carbon chain. So also the diazoketone is an intermediate, which we'll be knowing in a short while seeing the mechanism. The general reaction format goes like this. We take an acid, carboxylic acid, and then we expose it to SOCl2. Then it becomes actually this Cl reacts with one Cl reacts with HO, and it becomes HOCl, and then another Cl comes here, and it becomes RCOCl. Then this diazo compound also is exposed to this product, to this intermediate, and it becomes an amide. The amide, on reaction with Ag2O, which is silver oxide, it becomes this compound. And on reaction with this, with water, it becomes again a carboxylic acid, but with one increase in the carbon chain. See, here it's RCOOH, here is RCH2COOH. Suppose this is ethyl, this R group is ethyl, then this total group will become propyl. There will be one increase in the carbon chain. The group R in mother compound, this one, migrates with retention of configuration. This is actually very helpful if you go for optical isomerism or something like that. So for an optically active compound and conversion to its higher homologue. Higher homologue means generally this one, a higher carbon chain. So this on conversion to this is actually done with retention of configuration. All right. So if something is in a wedge form, it will remain in a wedged form. If something is in a dashed form, it will remain in the dashed form. Let's head on to the mechanism now. The mechanism's first step involves the diazo compound, which you have taken as a reagent. This change in the charges in the diazo compound, it leads to this negative charge being converted as a bond, which makes it triple bond, and then the positive charge remains as it is, but this double bond shifts to the carbon atom, and it imparts a negative charge here. Then what happens, this compound reacts with the given COCl, like RCOCl, because we get it from the thionyl sulfide, the thionyl chloride compound. So here it gets joined, because this negative part attacks the positive carbon here, which gets a delta positive charge due to shifting of electron cloud in the side of oxygen in this compound, and this becomes negative, which is quite expected because this electron cloud shifts in the side of oxygen, and then it gives birth to this intermediate. Then this chlorine joins with hydrogen to give HCl, which is removed later on, and the negative charge on the oxygen is imparted as a double bond here. So we get a double bonded CO here, and then again this moves, like the bond moves again towards the side of oxygen, the electron cloud, and it imparts a negative charge here. And this negative charged carbon, it imparts a double bond here. All this while, this positive charge in nitrogen was constant. This was constant, and then later on it helps, this positive charge actually helps in removing the N2 group, because N2 plus group is very, like, it's a very good leaving group, so it will leave from this compound, and then the double bond the electron cloud in the double bond will shift towards the carbon side again, and the negative charge will again shift towards the double bond, towards creating a double bond, and it will form a C double bonded O. Now this N2 plus will be removed as N2 gas, nitrogen gas, and on exposure to Ag2O, silver oxide, it will this bond here will shift towards this side, and the lone pair on the side of the negatively charged carbon will shift as a double bond here, which will form a ketene, which is actually like C double bonded O. Then on reaction with H2O will basically form the carboxylic acid, the final carboxylic acid. The mechanism was a little shrewd, whatever I could say, like a little big and tough, but it's fine. It's not really required in most of the cases, but it'll be fine if you remember it, because in very advanced level of questions it will be required. So now let's move on to the examples. So here we have some examples of Arndt-Eistert reaction. We can see that the first example is very easy, which is actually acetic acid on exposure, conversion through Arndt-Eistert reaction will become propanoic acid. Here, just one increase in the carbon chain. Then this compound on going through Arndt-Eistert reaction twice will give rise to two carbon in the carbon chain, two carbon. So this will increase the carbon chain by two methylene groups, and we can see that here. And the last example is a very typical example of a factory application of Arndt-Eistert reaction, which takes alpha naphthoic acid. All right, it is then passed through the reagents in Arndt-Eistert reaction, and then it becomes alpha naphthyl acetic acid, which is actually an addition of a methylene group in the COH group on the top side of the benzene ring on the right hand side. You can call it a right hand side or even a left hand side, because it's a very good mirror image, so it doesn't matter. But what matters here is that there's an addition of CH2, which is a methylene group, in the acetic acid chain, in the carboxylic acid chain. So that's it for today. I guess the notes were helpful for you. The points were highlighted, and I hope you get some help from it. Please do like and share the video if you genuinely love it, and subscribe to my channel if you're new. Bye bye.